Huixu. I'm from Beijing University of Post and Telecommunications. The topic of my presentation is Gaussian mixture model clustering algorithm for a probabilistic shaping 64-cam coherent optical communication system. The co-author includes Professor Yongjun Wang, Dr. Chao Li, and Professor Xiangjun Xin from Beijing University of Post and Telecommunications. My presentation will include 6 parts. Firstly, I will introduce some background of this research. Recently, some new services such as big data, cloud computing, 4K TV, virtual reality, Internet of Things, and so on. The development of these new services has led to an explosive growth of data traffic. Therefore, the optical communication is developing towards high speed, long distance, and large capacity. In order to satisfy the ever increasing demand for transmission capacity, high-order quadrature amplitude modulation, coherent detection, and digital signal processing are applied in the optical transmission system. However, there still have some problems. On the one hand, the gap between the capacity of optical transmission system and the channel limit still exists. On the other hand, for high-speed coherent optical communication system, the nonlinearity caused by devices and transmission link can severely limit the transmission distance as well as the achievable capacity. In order to solve the problems, probabilistic shaping and machine learning have attracted much attention because probabilistic shaping can reduce the gap between system capacity and channel limit, while suppress nonlinearity. Some machine learning algorithms, such as K-means, Gaussian mixture model, and SVM, can effectively mitigate the nonlinearity for optical communication. This paper will combine probabilistic shaping and the optimized Gaussian mixture model clustering algorithm for further introduction the system tolerance of high optical power. Next, I will introduce the principle of probabilistic shaping and Gaussian mixture model clustering algorithm with initial means. The probability distribution of the PS 64-cam constellation can be obtained by Maxwell-Boltzmann distribution, which is shown as the following formula, where xi stands for the ISPS 64-cam constellation point, and V denotes the shaping parameter. Next, I will introduce the principle of GMM clustering algorithm with initial means. GMM regards clustering data as mixed probability distributions from K-Gaussian distributions, which represent different classes. The GMM can be expressed as Formula 2, where Fk is the mixture coefficient of each Gaussian component. Phi is the Gaussian distance function. The EM algorithm is a common method to estimate the parameters of GMM. The EM algorithm includes 2 steps, exception step and maximization step. The EM algorithm works as follows. Firstly, randomly select the initial value of parameters fk and delta k, then start the iteration. Each step is to calculate the response of the submodel k to the observed data yj according to the parameters of the current model. M step is to calculate the model parameters of the new iteration. Finally, when the formula 7 is satisfied, the iteration ends. If the formula 7 is not satisfied, turn to step 2 and continue iteration. The distribution of PS64 cam signal is non-uniform. The probability of the outer points is far less than the inner points, as shown in Fig 1b. In Fig 1a, some outer points will be mistakenly clustered to other cluster under GMM clustering algorithm. In order to deal with this problem caused by the uneven distribution of PS64 cam, we initialize the mean of each Gaussian component with the PS64 cam standard constellation points. The mean of each Gaussian component obtained under GMM clustering algorithm with initial means is shown in Fig 1b. Next, I will introduce the experiment setup and the results. Figure 2 depicts the experimental setup at the transmitter side. At the transmitter side, the PVRBS is generated by MATLAB. The non-uniform 64 cam signals are generated by a constant composition distribution method and mapped to 64 cam constellation. Then the signals are fed into an AWG to generate electrical signals as drive signals of IQ modulator. A laser is used to generate continuous optical wave with length of 100 kilohertz and the wavelength of 1,550 nm. The transmission link consists of 5 spans, single mode fiber with length of 65 km, and each span followed by an ADFA. At the receiver side, a laser with line width of 100 kHz is used as the local oscillator for coherent detection. Then the optical signals are detected by the coherent receiver. The offline DSP include 10 steps. The Q factor versus launched optical power for PS64 cam and uniform 64 cam after 375 km SMF transmission is shown in Fig 3. The performance of PS64 cam is better than uniform 64 cam within the entire measurement launched optical power range. With the aid of the GMM clustering algorithm with initial means, the PS64 cam can obtain 0.53 dB Q factor improvement compared with the traditional minimum eluding distance-based decision as the optimal launched optical power of -3 dBm. However, the uniform 64 cam can only obtain 0.32 dBq factor improvement at the optimal LOP of -1 dBm. The results show that the combination of PS and the GMM clustering algorithm with initial means can effectively mitigate nonlinearity and improve the performance of the system. Next, I will introduce the conclusion. We initialize the mean of each component of GMM clustering algorithm according to the characteristic of PS64CAM. Experimental results show that the combination of PS and GMM clustering algorithm with initial means can significantly improve the performance of the system. Thank you.
Thank the speaker. Question.